solve it as we go through. And there are the FAR poster at the front is related to today. I'll have to maybe at the end show you what I was thinking when I made the reminder that's up there. All right, so segments that intersect in circles, we're going to have secant segments and tangent segments in our diagrams. The first one we're going to start out with would be two chords. When two chords intersect in the circle, there's actually, if we connect, there will be two similar triangles. And what I'm doing here is kind of showing you where the theorem's coming from. Okay, so just listen with me here, or think with me. If I would connect these two and these two, the ends of those chords, we have two triangles. Now I said that they're similar. So what would convince you that they're similar? Well, these two angles are the same. That's probably not quite enough because we need angle-angle similarity. If I look at this arc, inscribed angle over here is the same as that same arc, the inscribed angle going this way. We had a theorem yesterday that if those two inscribed angles intercept the same arc, they'll be congruent. So now the two triangles have two angles congruent in them, so angle-angle similarity is going on. Side lengths, when they're similar triangles, the sides were in proportion, so I can make some ratios. Let me label a little bit. A, B, C, D. I really don't need those other two sides. So the length of A would be in ratio with C. I'm picking up the same two angles to make sure I match up the sides correctly. So A and C will be in a similarity ratio, the same as D and B. If I cross multiply, that tells me that A times B will always equal C times D. Let's put some numbers up there instead of just variables. Okay. The first reminder up there, I guess I did set it up right, is set up the way that I just did that. Let me put some numbers in here instead. Let's make the small one 1/3 as much. So if this is 1, then the matching side would be 3. This would be, let's say, 2 and 6. So notice that 3 over 1 and 6 over 2 are the same. When I cross multiply, 3 times 2 will always equal 1 times 6. 6 equals 6. The theorem is going to tell us that if you multiply this number and this number, it will always equal this one times this one. What it's based on is the similar triangles and the ratios and cross multiply. So as I show you the theorem, what I just went through is just to kind of show you that there is a reason for there is a reason for this theorem, and it's actually the similar triangles that I was just showing. The theorem wording is if two chords intersect in the interior of a circle. So that's your hypothesis. Draw yourself a circle with two chords intersecting. They don't have to intersect at the center. It'd probably be better if you don't make them intersect at the center. It says then the product of the lengths of the segments of the chords are equal. The product. So if you multiply the lengths of the segments on each chord, they will always be equal. If you want to use the labeling that goes with what's on the screen here, label your points. It says on one segment, if you multiply AE and BE, that will be the same product as CE times ED. For it to match what I have on the wall, we would have on one chord A and B, and on the other chord C and D. So on the wall, I have stated it as AB equals CD. So I guess you could choose which way you want it to appear. looking at the screen? And let's try a sample. Find the value of x. How long is this segment? The theorem says products. So that segment times the other piece on that same chord. So x times 14 will equal the same as 7 times 10. The solving is probably not the issue, setting it up right is the issue. So x times 14 equals 70. 70 divided by 14 is 5. Now the directions say and find the length of each chord. Okay, so what it's asking you to say is that FE is 17, GH is 19. When you find how long they are, you don't multiply. But if this was 14 and we just found this piece to be 5, that's a total of 19. So that's what the directions are saying. Find x and find the length of each chord. Okay, marker boards then, to give me the final answers on this one. Find the value of x and the length of each chord. Marker boards. Chord also. Chord lengths are not right. I think you multiply.
Oh, okay.
I didn't really look, what did you have? I was kind of looking at hers. 6 times 5 has to equal 8 times x times for the theorem. Then once you find the length, or once you know what x is, to tell the length you're adding together. Okay, here you go. Abby and Jack. Okay, you set up multiplying for the theorem. Okay, that's how you figure out what x is, multiplying. But then the length of the segments, you're just adding the two segments together. So AB was 11, and then DC would be 11.75. Okay, follow-up questions? Yes?
Does it matter if you put like the 6 over x or the 5 over x?
6 over x or 5 over x, depends what you set it equal to. Okay, so tell me one way, go completely.
I did 8 over 6.
8 over 6.
And then 5 over x.
Over x. So did her cross product work out right? 30 equals 8x, 30 equals 8x. Okay, so that would be an okay setup, yes. Now that one would not be, I'm trying to think of triangles. If I did this way, I'm just thinking through the triangles that you're using, this angle. Okay, so 8 and 6, those were matching sides, 5 and x were. Okay, so then you asked, could you put 5 over x?
6.
or 6, how else would you want to go? 6 over x, and then 8 over 5. That will do the same thing, because that would give you 8 over, let's see, you wanted to do this, right? That would give you the same cross products, so it's going to give you the same answer. This one doesn't really follow a theorem that I'm aware of, okay, because you're putting a ratio of those two sides. But back in that chapter, there were students that were doing that kind of thing. So it works, it just doesn't follow a theorem if you were trying to support it. Okay. Other questions? Okay. All right. This says, in 1901, divers near the Greek island of Antikythera discovered several fragments of ancient items. Using the mathematics of circles, the scientists were able to calculate the diameters of the complete discs. So how can you find the diameter if you don't have the complete circle? Now, we did the construction yesterday. How did we find the center of the circle, even if we didn't have the whole circle? Tina, you're having trouble today. How did we do that construction yesterday? We did it twice, once with the whole circle and once with just an arc. Okay, 2 chords, and what did we do to the chords? Okay, perpendicular bisectors. So making a chord, doing the perpendicular bisector, making another one, doing the perpendicular bisector. Okay, so that was one way to find the center. We're going to use something similar to that on this story then. To determine the diameter of a broken ancient disc, archaeologists drew a perpendicular bisector of a 12-inch chord. Now, they only drew one, and then from that they calculated the diameter. They didn't necessarily locate the center, but they calculated the diameter. Okay, how did they do that? Let's finish drawing the rest up here. Okay, so I'm going to just dash. We're thinking about a circle here. Okay, if I have this 6-inch chord, and we're doing the perpendicular bisector of it, we don't know the length from this intersection on out, but that added with 3 would be the whole diameter, because a perpendicular bisector of a chord is always a diameter of the circle. So we can calculate based upon what we are doing right now. 6 times 6 has to be the same as 3 times x, just using your 2 chords. 6 times 6, the product from one chord will equal the product from the other chord. So 36 divided by 3, x is 12. So this part is 12, and then we have 3 more added on to it. The whole diameter is 15 inches. We didn't locate the center, but we know how long the diameter is based upon what we're doing today. See the connection between yesterday and today? Same idea with the perpendicular bisector going through the center of the circle. Need something written down from that one, probably? There's a problem like that on homework. Okay, let's see what's next. Okay, we did that construction yesterday already. If you didn't have a question on that, let's talk about things related to the next theorem. This isn't the theorem yet, but in the theorem it's going to mention secant segments and external secant segments. Okay, a secant, if you recall from our first day in this chapter, whatever day that was, a secant is a line that goes through the circle at 2 points. Okay, I didn't completely draw the whole line, I guess. I just made it go through the circle and stop. Because secant segment is a segment of a secant with at least one endpoint on the circle. So secant segments would be like segment PM, or segment NM, or segment KM, segment JM. All of those are secant segments. A couple of them are external secant segments. If you think what external means on the outside, So the external secant segments lie in the exterior of the circle. One endpoint is on the circle. So just segment NM is an external secant segment, and JM is an external secant segment. That vocabulary is needed to understand what this theorem is saying. This one has two secants. So as you draw your picture, make those two secant segments. They have to intersect in the exterior of the circle. Now this has segments you can multiply together, like that last one. Certain segments multiplied will be equal. So what segments are they? By their notation, AE and BE multiplied together. And then CE and DE multiplied together. Now in words, that's the product of the lengths of one secant segment and its external secant segment. So the whole red secant segment times the external part of it. And the whole secant segment times the external part of it. And what is that based on? That would be based on similar triangles also. Not drawn exactly the same way I did with the two chords, but the same idea that you can set up ratios to see where these products come from. I didn't take time to go through that. Some of you don't like it when I do that anyway. Now to match up with the wall, the second one down over there, A and A plus B, that would have to be set up with A on the outside, B as this like in-between part, C on the outside, and D as the in-between part. So on the wall, we take the external part times the whole secant segment. That product will equal on the other one, the external part times the whole secant segment. So that's what goes with the second line on the wall. So if you want that to match up with the wall, there it is. All right, let's try some example problems. Everybody got what they need? Okay, so how would you use this? Find the value of x and the length of each secant segment. So two secants. So it said multiply the exterior part times the whole secant segment. Multiply the exterior part times the whole secant segment. So 8 times what? What's that whole secant segment? What's the length from here to here? It's not 8 times x. It would be x plus 8. Just like what's this whole segment? 9 plus 7, 16. For the theorem, we need to multiply those sections or those segments together. So you would take 8 times x plus 8, and you would take 7 times 16. Those are the parts that would multiply together. Distribute. Subtract 64. Divide by 8. X was 6. The directions still say the length of each secant segment. It's not talking about the exterior part, it's talking about the whole, like EG. So EG would be 8 plus 6, and ED would be, or we already did, 7 plus 8 is 16. So 16 and 14 are the lengths of the segments. All right, let's try another one. And you have to pay attention to how the information's given. Did they give us the whole thing, or did they give us the parts to it? All right, set this one up. and multiply, and did you find the length of each secant segment? All right, the answer's here. Z was 14, so your lengths were 39 and 27. Give me a thumbs up or down, so I didn't get all the way around. Is it right? Okay, that's pretty good. You know what you need? Got it? All right, there is one theorem about a tangent segment. So to clarify, a tangent segment is a segment from a tangent line, and it has one endpoint on the circle. So these pictures are showing tangents, not secants. This one kind of looks like it would go across the circle, but I whited it out so it stops. The next theorem deals with a tangent segment and a secant segment. So it has one secant, one tangent, and my tangent doesn't look too good up there, so make yours go out far enough that it looks like a good tangent. Again, I had to white it out because it was going to hit the circle twice. All right. The product that you were using on the secant still applies here. You'll take the whole secant, AC, times its exterior part. Now on the tangent, there are no two different segments. So you end up taking the tangent part times the tangent part. So that ends up squaring the tangent segment. So the wording says if a secant and a tangent intersect in the exterior of a circle, then the product of the lengths of the secant segment and its external segment equals the length of the tangent segment squared. On the wall, that's the third one down over there. The way that it would be labeled to match with the wall, to do A and A plus B, the A's on the outside. So A, B, and the tangent part is C. So on the wall it says take A times A plus B, and that will equal the tangent part C squared. In other words, C times C. Got it down? Let's try an example or two. Okay, so notice where you have a secant and a tangent. Okay, the theorem says you can take on the secant the exterior part times the whole thing. On the secant, the exterior part times the whole secant segment, and that will equal the tangent part times the tangent part. The tangent part squared. That's where the variable is. We're going to have an x squared. So this one you should have 5 times 20 equals x squared. 5 times 20 is 100. Square root of 100. We want the negative part. X as a negative length doesn't make sense. So just a positive 10 would be the correct answer. So X is positive 10.
So like if you were to put the positive and sign before the time.
When you're solving it, I would say technically when you solve it, it's okay, but then to give the final answer, you should probably just take it to x equals 10. I wouldn't take off a lot, but yes, I would probably take off some because negative 10 doesn't make sense. Is that what you were going to ask, Abby?
Yeah.
Okay. All right, let's have you try another one. The variable's in a different place this time. It's still a secant and a tangent. This one doesn't come out a nice integer. 51 divided by 7 doesn't come out to a whole number. They gave me a fraction. 2/7 as a fraction, I don't know. Round to 0.3. So 7.3 approximately, if it's in there's 10. Any question on that one? Notice you didn't have to worry about the positive negative because of where the variable was. It wasn't on the part that got squared. Now, I'm just going to make a revision to this one and let you think about how it would be. What if the y is here and the 7 is here? How would that change the setup? What would you be multiplying? Y times y plus 7 equals 10 squared. Y squared plus 7y equals 100. How would you solve that? That's one of those quadratic formula problems. So you would have to subtract the 100 before you pick out your A, B, and C to use on the quadratic formula. I'm not going to have you completely solve that, but just for you to be aware, there might be that type coming up depending upon where the variable is in the problem. Okay. As far as our lesson, that's all I had. On that poster, there's one more type. The bottom says A equals C, and that type, I don't know, I have a blank screen, but that type actually goes back to something we had in an earlier section, where it had a tangent and another tangent. Maybe section 2, it said those two tangent segments are equal, but this segment would equal this one. That's why I put on the wall A equals C. Because basically that's, instead of using tangents, it's using secants. If we applied really that last theorem, we probably would say tangent part squared would equal tangent part squared. But if you do the square root of each of those, it does end up with each of those tangent segments being equal. Which theorem was it that said those tangent segments are equal? That was actually theorem 11.3, or 11.1.3. So that last thing on my far poster is about the two tangents. All right, so since we have a quiz, we probably should end there. Questions on your lesson part? Okay, the problems that you'll do when you're done with your quiz then are on page 795. I don't know why I did this. 33 to 36. Last homework assignment? Oh, probably next Tuesday. Oh, I know why I had it listed. I wrote something down wrong. This, okay, the end of this, I don't know if I typed it right in the computer. I think it's 45. And you might check on your backpack. Did I have that right? There's not much on Friday.